Hi, welcome to AP Chem Speed Review. I'm Jim Burnham. We're talking about Unit 7, which is on equilibrium. It's typically just under 10% of a normal AP exam. College Board describes this unit this way. Students will construct equilibrium expressions from reaction equations. Students should illustrate the dynamic nature of the chemical reaction, portraying both the forward and reverse rates of reaction equations. We look at graphs that depict this, and especially we're going to look at equilibrium expressions. And we're going to use experimental data to calculate what's known as the reaction quotient and equilibrium constants for a reaction. Then, using something called Le Chatelier's principle, we will talk about what happens to a system in equilibrium when stress is placed on it and how it responds to those stresses. All right, so the bottom line, equilibrium is a reversible dynamic process. That means it can go in both directions. So we're talking about reactions where the reaction can go in the forward direction, and it can also reverse and proceed in the opposite direction. And what happens at equilibrium is that those processes happen simultaneously at equal rates. We're going to learn to write and evaluate equilibrium expressions. Okay. Many chemical and physical processes are reversible, and which means they can go in either direction, and they will eventually settle down into an equilibrium where both the forward and the reverse reactions are at the same rate. And so the concentrations of both the reactants and the products stop changing. We see reversible processes in many places in nature. We see the evaporation, for example, and condensation of water. We see the absorption and desorption of a gas. We see the dissolution and precipitation of a salt. One important reversible chemical process is the transfer of protons in acid-base reactions, which we will look at later. And we've already talked about the transfer of electrons in redox reactions. So remember, reversible reactions are reactions that don't go to completion. And remember, we talk a lot about reactions, especially in general chem, and we assume that they go all the way to completion, but in truth, most reactions don't go all the way to completion. They may proceed a long ways toward completion, but very often the reaction will reach a point of equilibrium where the rate of it going in the forward direction is balanced by it going in the reverse direction. And so we represent reversible reactions with these arrows in both directions. So most reactions, or at least many, don't go to completion as we've been assuming. They can be reversible, in which the conversion of reactants to products, which is the normal direction, and the conversion of products back to reactants occur simultaneously. So here is this reaction in the forward direction, where SO2 and O2 are making SO3. But also, as this product increases, at some point, that product will begin to decompose back into the reactants. And so we can distinguish the forward reaction from the reverse reaction. And we say at equilibrium, no observable changes occur. And that's because the forward and reverse reactions are both preceding. And so you're going to have some of the reactants and products simultaneously present. The concentrations or the partial pressures, if we're talking about gases, remain the same. Starting with S and O2 only, well, that's not at equilibrium, so that's going to react and create some SO3. Or if we start with just SO3, the product, not at equilibrium, it will break down and decompose into SO2 and O2. And at equilibrium, we'll have some of each. We'll have some reactants present, we'll have some products present, so all three will be present at equilibrium. It's important to remember this is a dynamic equilibrium. That is, it's not that the forward and reverse reactions stop, it's just that they proceed at equal and opposite rates, resulting in no net observable change. So imagine you've got an escalator moving down at a certain speed v, and you have a girl moving up that escalator at speed v. She's going to look like she's standing still. Right? She's not, her position isn't going to change. But of course, she's moving up and the stairs are moving down. It's just that together the rates balance each other out. Another way to think about it is if you've got a bunch of cars going onto this side of the city and a bunch of cars going on this side of the city, and if the net outflow equals the net influx, then the overall population on both sides of the bridge is going to remain the same, even though, right, cars are streaming across in both directions. So when we look at a graph of concentration or partial pressure or reaction versus time, we can see how this can be used to describe chemical equilibrium. So, for example, here's the forward rate, and initially the forward rate is going to be quite high as reactants are converted into products. But as the products grow, more and more of them will be converted back into reactants, and eventually the forward rate of product production and the reverse rate of product decomposing back to its reactants, that will become equal. And so the forward and reverse rates will remain the same. And at that point, they're equal. If we look at the amount, at the beginning, we're going to have a lot of reactant. At the beginning, no product, right? And products are going to decline as the reaction proceeds. Products are going to increase as reaction proceeds. But at some point, neither will change. At some point, the products will level off and remain the same. The reactants will level off and remain the same. And at that point, we've reached equilibrium. So one of the important concepts is that we can establish equilibrium from either the forward or the reverse direction. So we can start with SO2 and O2, and those can react. So this is where we have a lot of reactant, and we start with zero product, and that will the reactants will drop in concentration, the products will grow in concentration until they level off. But we can also start by just having all products. Here's all SO3 and zero reactants. And what's going to happen? Those products are going to then decompose back into the initial reactants. And again, we'll get a point where we have a stable concentration, unchanging concentration of both reactants and products. So we can establish equilibrium from either direction, by starting with all reactants and no products, or even by starting with all products and no reactants. Either way, it will shift back into equilibrium. So let's look at the direction in which a reaction proceeds and the relative rates of the forward and reverse reactions. So now it's important to remember, even though the rates of the forward and reverse reactions are equal, that's the definition of equilibrium, that doesn't mean the concentrations on both sides have to be equal. So at equilibrium, you might have 1% reactant and 99% product. Or you might have 99% reactant and only 1% product. You may also have 50-50, but that is a rarity, not the norm. So don't think that equilibrium means you have equal amounts of reactants and products. The equilibrium point or position may be shifted very, very close to products, or it may be shifted very, very close to reactants. So that's what we talk about. We talk about which side is being favored. Does this reaction, does equilibrium favor the production of products, or does equilibrium favor the production of the reactants? If the rate of the forward reaction is greater than the reverse reaction, then there will be a net conversion of reactants to products before we establish equilibrium. If the rate of the reverse is greater than the rate of the forward, then there's a net conversion of products back to reactants. At equilibrium, we have both of those rates being equal. Imagine you have two armies with cannons, and they're firing cannonballs at each other. And let's say one army has 10 cannons and the other army only has 2 cannons. Well, initially, the army with 10 cannons, right, will fire more cannonballs over. And then the other army will take those cannonballs, if they didn't bring enough of their own, right, and they'll start firing them back. And initially, the side with 10 is going to be raining a lot more pain down than the army with 2 can respond. But eventually, this side will run out of cannonballs, and then it will be this side will be able to shoot 2 at a time, and then the forward reaction, even though they have 10 cannons, will only be able to shoot 2 back. And at a certain point, you'll get a moment where, or a situation where both sides are shooting the same number of cannonballs at the same time, and there's no net change of cannonballs. So even though this side started with more cannons and more cannonballs, eventually you reach a situation where the rate of the exchange of cannonballs is equal. Chemical equilibrium. It's a reversible reaction in which the products can react to reform the reactants. And when the forward reaction equals the rate of the reverse reaction, the concentration of products and reactants remains unchanged. So we can describe this situation with what's known as the equilibrium constant. Now remember, before when we were talking about rates, we can connect this if we want to with rates. We talked about how we can describe a rate, the rate of a forward reaction, as a constant times the concentration of the reactants. And we can describe the reverse rate, right, as a constant times the reactants going in this opposite direction, the reverse rate. When the system is equilibrium, as we said, the forward rate is going to equal the reverse rate. So we can substitute those two expressions as an equality and say the forward rate equals the reverse rate expressed this way. Well, then we can rearrange our constants, get them on the same side, and so we now have a new constant that is described as products over reactants. And that's our new constant. And so that's the way we can develop the equilibrium constant for this reaction. So in general, when we have a reaction, coefficient A, coefficient B, coefficient C, coefficient D, and we have A plus B yielding C plus D, we can define the equilibrium constant as the concentration of the products raised to their coefficients over the concentration of the reactants raised to their coefficients. This is known as the mass action expression. It's valid for all reactions. So this is going to be our universal expression for equilibrium. It's going to be our products over our reactants. How would we write an equilibrium constant for this expression? Right? Well, we're going to say, right, Kc is equal to, we're going to say the concentration of this times the concentration of this over the concentration of this, or this. Remember, equilibrium does not mean we have equal amounts of reactants and products. It could be, but more likely it's going to be shifted in favor of one or the other. Depending on the value of K, we can see that the equilibrium can be shifted in favor of products. That's where K is going to be much larger than 1. Or it's going to be shifted in favor of reactants, and that's when K is much, much less than 1. Or we can have a lot of both, and that's when K is approximately 1. So now let's take a look at what's known as the reaction quotient and its relationship to the equilibrium constant. A system in equilibrium depends on the relationships between the concentrations or partial pressures of the chemical species and the equilibrium constant K. We can also represent the reaction at any other time, not just at equilibrium, by what is known as the reaction quotient. And we can look at the relationship of the reaction quotient to the equilibrium quotient. So the reaction quotient, Q, describes the relative concentrations of the reactant species at any time, whereas K, remember, describes the concentrations at equilibrium. For gas phase reactions, the reaction quotient can be written in terms of pressures. So we would say instead of Q of concentration, QC, we would write it as Q of P. So just like the reaction constant, we can write the reaction quotient in the exact same way. So for this typical reaction, we're still going to put products raised to their coefficients over reactants raised to their coefficient. And this is, we call Q, and it's equal to this concentration at any time in the reaction, whether it's at the beginning, middle, end, it doesn't matter. So this is a more general expression. We only call it K when the reaction is known to be at equilibrium. So at equilibrium, our K and our Q values will be equal to each other, whether we're looking at concentrations or whether we're looking at partial pressures. So remember, Q is products over reactants. And the more products we have, right, the larger this quotient will be. And the more reactants we have, the smaller Q will be. And here's the thing to know, is that if Q is very, very small, it means that we have a lot more reactants than products. Well, then Q wants to tend towards K. So it's going to form more products to get larger. If Q starts out too large, then that means that we have too many products. Remember, products are high. So if Q is high, products are high, therefore this reaction is going to shift away from products toward reactants, make more reactants until Q equals K. And the moment Q and K are equal, then the reaction stops shifting and is at equilibrium. So remember, Q has the exact same form as K. The only difference is that the Q value is not necessarily an equilibrium value, whereas K is the equilibrium value. So remember, no matter at what concentrations we start at, whether it's all products, all reactants, or some of both, once equilibrium is established, the value of K is always the same. That's why we call it the equilibrium constant. The only thing that changes K is temperature. So very often when you get an equilibrium constant, it will tell you at what temperature that applies. We don't often use the temperature, but it will say at this temperature, say 300 Kelvin, this is the equilibrium constant. So let's look at writing an expression for K based on this reversible chemical reaction. Okay, reactants here, we've got products here. Again, so we're going to take products raised to its coefficient over reactants raised to their respective coefficients. That's the Q expression. How do we calculate K? Well, if we are given the equilibrium concentrations, we simply plug those in to our K expression. So if we're given these concentrations, we plug those in, we do the appropriate squaring or cubing or whatever, and do the math, and that is our Q value. One thing to notice about Q is that Q does not have any units. For reasons I can't go into right now, just take it as a given, Q has no units. All right, let's look at another example of calculating equilibrium concentration. We're given the concentration of these two species, but we don't know the concentration of HI. But that's okay, we plug this into our expression, right? We take these two givens, we plug them in down here. Oh, and we are given the K value here, so once we plug everything in, we can now solve for HI. And we can do that here by taking the square root here both sides. And this gives us our concentration of HI. Okay, again, quick review. Equilibrium constant is known as Kc, or if we're dealing with gases, Kp. We write this as products raised to their powers over reactants raised to their powers. We can also use, as I mentioned, Kp for gaseous equilibria. Because as we calculate Kc, we need concentrations, and that can be hard to find for a gas. So we can also write the equilibrium constant as a partial pressure expression instead of concentrations. And it's the same thing. So here we would write this is in terms of concentration, right? The concentration of our products raised to its coefficient over the concentration of our reactants raised to their coefficients. Or we can write these in terms of partial pressure. And it's the partial pressure of this raised to its coefficient plus the partial pressure of these two reactants raised to their respective coefficients. And partial pressure is defined as the molar fraction of each of these species times the total pressure. So you find out, if this is say 1/4 of the total moles, then it would be 1/4 times the total pressure in the container. And if this has the 1/4 of the moles, it has 1/4 of the total pressure. So that's how we write and calculate these expressions. So we can do it for Kc or Kp. Remember, Kp, just like Kc, always has the same value provided we don't change the temperature. And it has the exact same format, except we're going to use partial pressures instead of concentrations. Remember, the reaction quotient doesn't include substances whose concentrations or partial pressures are independent of the amount, things that don't change, such as solids and liquids. So solids and liquids will not appear in equilibrium equations. We'll simply leave them out. So for example, if we have an equilibrium, writing equilibrium law for this, okay, we have these two ions, and then we have a solid here. Well, we're not going to include this, so we're going to write this as just 1 over, and then we'll put our reactants here. Remember, it's products up here raised to their coefficients, but here we don't have any. So we're just going to put a 1, and then divided by the reactants raised to their coefficients. Here we have an aqueous solution here, plus water, plus some more ions here. So again, we're going to ignore the water. So we're going to put products, their concentration, over the reactant that is in solution, over its coefficient, and we're going to ignore the water. So we leave out solids and liquids. Okay, here's a great summary of a bunch of things having to do with reaction constants. There's going to be lots of problems where we calculate the equilibrium constant from various givens based on experimental observations. So they're going to give us various concentrations or various pressures and then ask us to calculate the Kc or the Kp. So here would be a typical kind of problem. So here is the reaction. Here's what we're starting with initially. So initially we're starting with 1 mole and 1/3 of a mole of these two species. Initially there's no product, but at equilibrium we have this distribution, and to determine the Kc value we're simply going to plug all of those values in, right? So we're going to take products over reactants. We're going to get our Kc value. We have here's our reaction. Here is our at equilibrium we have our equilibrium concentrations. We simply plug those into the Kc expression, which is going to be, right, products squared over our reactants taken to just the single power. But since we're multiplying them together, this is going to give us this expression. All right, let's talk about the magnitude of the equilibrium constant. K gives us in one number a way to instantly know whether we're going to have a lot of product or very, very little product, and mostly reactant. And so the value of K tells us at a glance what to expect. And what we see is if an equilibrium reaction has a very large K value, then it's going to proceed essentially 100%, or very close to that. Reactions with very small K values will barely proceed at all. Remember, K is product over reactant. So if the product is way, way big and the reactants left are way, way small, that's going to give us a very large K value. In contrast, right, if reactants are way, way big and very, very little product is formed, then our quotient is going to give us a very small number, which means the reaction barely proceeded. So the magnitude of K, again, tells us the relative proportion of products to reactants. Super large, much more product. Super small, much more reactants. This should say very, very small. Or if it's close to 1, they're going to be approximately equal. All right, so here are some calculations of K. If we know the initial concentrations and we know the equilibrium constant, and this is going to use what's known as an ICE table. An ICE table is we're going to track the initial concentration, then we're going to track any change, and then we're going to finally get the concentration at equilibrium. So initial, change, and equilibrium. In this particular reaction, we're starting that the concentration of H2 and I2 are 3 molar each. So at the beginning of the reaction, nothing's happened. So we're going to have 0 concentration of product and a 3 molar concentration each of our reactants. Now, how is this going to change as the reaction proceeds? Well, these two reactants are going to react, right? Their concentration is going to decrease, and they're going to form products. For every molecule or mole that this goes down, right, this is going to go up. So as these decrease, and they'll decrease in a 1-to-1 ratio, it's going to form product at a 2-to-1 ratio. So when we track this change, we'll just call it, since we don't know what it is, we'll just put a variable in there. We're going to say this is going to go down by X. And this is going to go down by X concentration. And this is going to go up by twice as much of X because of this is our molar ratio. And so then we just calculate our concentration. We just add these two together. 0.3 molar minus X, 0.3 molar minus X, and this is 2X. And then we put each of these final concentrations into our K value, and we solve for X. Once we solve for X, then we can subtract X from this, subtract X from this, and then multiply X times 2 to get the concentration of all of that. So that's the setup, that's the math. You can pause if you want to review that. Again, there's other ways they can ask these. They can give us the initial concentrations plus the final concentration of product, and then have us calculate what X is. And again, we have to set up our ICE table and start solving for what we can. So again, I won't go through the math on this, but this is another way that the problem can be asked. Okay, remember the reaction quotient Q is just like K, except we just do that at any concentration, whether it is or is not at equilibrium. Sometimes we have to calculate Q first to figure out which way the reaction is going to proceed. Do we have more product? Do we have more reactant? And so which way is it going to shift? So again, I don't want to spend too much time on all of these. Sometimes you'll get to a situation where you can't solve a problem by taking the square root of both sides, and you have to use what's known as the quadratic equation. But on the AP exam, you will never have to use the quadratic. So there will always be a workaround. Either you can take the square of both sides, or as we're going to see, sometimes K is so small that the change in X is basically negligible and can be ignored. So that's, just don't want to spend too much time on all these problems. So let's look at the properties of the equilibrium constant and how we can manipulate them if we change the reaction. So we can represent a multi-step process with an overall equilibrium expression using the individual K expressions for each reaction. So let's look at when we take a reaction and we reverse it. If we reverse the reaction, right, we're going to be flipping the order of the reaction of the products and the reactants. And so that is going to have, the effect of inverting the K. Now this is not like delta H, right? In delta H, remember Hess's law? If you reverse a reaction, you reverse the delta H. So if the reaction in the forward direction gives off 100 kilojoules, in the reverse reaction, right, it's going to require 100 kilojoules. But reversing a reaction, because it is a quotient, right, because it is products over reactants, when we flip that, we are actually going to invert that quotient. So let's look at it so the K expression for this would be, right, C plus D concentrations over the reactants. But if we flip this and we put C and D as the reactants, right, now they're going to go on the bottom, and A and B, which were the reactants over here, they're now the products. So this new reaction is it's the inverse of this reaction here. So this new constant is going to be this new equilibrium constant is going to be the inverse of the old equilibrium constant. So when we flip a reaction, we invert our K value. What about if we take a reaction and we multiply it? Well, we're going to see if we multiply by a factor, say, of C, it's going to raise the entire C value by that multiple. So if we double a reaction, we're going to raise the C value to 2. We triple the reaction, we're going to cube it. and we can see why. So let's just look here at a generic reaction, right? Products over reactants. Well, if we triple everything, right, now everything is going to be tripled. Cubing, we're going to cube all of these, which is the same as cubing our original K. So if we triple a reaction, we cube the original K. You double a reaction, you square the original K. If you cut the reaction in half, again, you're going to multiply this by it's just going to be K raised to the 1/2 power, which is the same as taking the square root. How about when we add two reactions together? Well, the K of the overall reaction is the product of the individual Ks. So let's say we have two reactions, A plus B yielding C and D, and then C and E yielding F and G. Well, what we're going to see when we add all these together is that the C's are going to cancel out, and what we're going to get is essentially the K value of the first reaction times the K value of the second reaction. So the K value of the whole of all the steps added together is going to be the two K values multiplied together, not added together, multiplied together. And since the expressions for K and Q are in the same mathematical form, everything we do to K we can also do to Q. So if we have if we invert a Q value, it inverts the Q expression, 1 over Q. If we multiply the expression by 2, then we raise the Q value by a square. If we multiply it by a third, right, then we would take the cube root. So anyway, everything we do to K, we can do to Q. All right, let's look at more particularly calculating equilibrium concentrations. So this is going to take us to our friend the ice table. As we've already alluded to, we can identify those concentrations at equilibrium based on the initial conditions and the equilibrium constant. So we can predict the concentrations or partial pressures of species at equilibrium if we're given the balanced reaction and the initial concentrations and the appropriate K values. So these Q and K expressions are powerful predictive tools for telling us what's going to happen. Once we know a K value, we don't have to run the reaction. We can know what the equilibrium concentrations will be just by plugging in the values. Kp is going to be our partial pressures rather than concentrations, but we build the expressions the same way. Remember, for gaseous reactions, we can either use Kp or Kc. And notice that Kp and Kc for a gaseous reaction may or may not be the same. So don't expect them always to be the same. They only will be if there's not a change in the number of moles. For solution reactions, we have to use Kc. Either way, the calculations are basically the same. So we can either calculate K from known equilibrium concentrations, or we can calculate one of the equilibrium concentrations given a known Kp or Kc. So when we know all the concentrations, then we just plug them into the mass action expression and solve for K. But sometimes they can break that up. So I'm going to give this various examples. I'll go through them quickly. You can pause these if you need to. But given this expression, here's our equilibrium concentration of our reactant. Here's our equilibrium concentration of our product. We just put it into our expression and we solve for K. This takes us to our ice tables when we are given both initial concentrations and final concentrations. So if we have both conditions, initial and final, then we're going to have to set up our ice table and find out whatever's missing. So here's how you set it up, and so we can calculate these. And then given those, we can just plug those into our expression for K and solve for K. So I don't want to spend too much time on all this. There's just lots and lots of practice problems that you can do, but I want to just get to the main concepts. So if you want to stop and work through these, you can. Very often we can solve for x by taking the square root of both sides, so it looks like a quadratic, but when you take the square root of both sides, it does not turn out to be a quadratic. All right, we're just about done with the sample problems here. Again, I just don't want to take the time to go through them. If you want to, just pause and work your way through them. If our k value is very, very small, then our change term, our x term, is also going to be very small. And we can then ignore it when adding or subtracting from the initial concentration. And that is often another way you can avoid having to use a quadratic. 2a goes to b. We know that we're starting with 0.2 atmospheres. Our k value, look at this, is super, super tiny, which means the amount of this that's going to change is essentially 0. So when we subtract this super tiny number from 0.2, it's going to remain essentially 0.2. So it's just like if we start with the entire population of the United States, 350 million, and you subtract one Jim Burnham, it's still going to be 350 million. Right? I didn't change the overall population enough to matter. Same thing here. This tiny little change in x, we can still say is still 0.2. And thus we can put that into our expression and solve for it without having to use a quadratic. All right, let's look at representing equilibrium with a particulate model. Let's look at this particular particulate diagram. Here we have, so here we're starting off the concentration of N2O4. So this is our reactant initially, and here it's just pure reactant. Okay, NO2. Okay, this is just pure product. But at equilibrium, we're going to have some of both. So our concentration of our reactant is going to go down. Our concentration of our product is going to go up. At some point, they're going to reach equilibrium, and we're going to have some of both. Right. So here is the beginning of the reaction. If we started with all reactant, here would be if we started and ran the reaction, in reverse and started with all product. This rate, the forward reaction is going to decline. The reverse reaction is going to increase, and at equilibrium, the rate of the forward and reverse reactions are going to equal each other. So we can use these particular representations to look at the relative numbers of reactants and products, both prior to and at equilibrium. Now this takes us to one of the more important topics in this unit, which is called Le Chatelier's principle, which explains what systems at equilibrium do, how they respond to stresses that take them out of equilibrium. And the answer is that they will respond in a way to counteract the stress and try to re-achieve equilibrium. We define stress as anything that takes the system out of equilibrium. And Le Chatelier says that the system will counteract that stress and try to return to equilibrium. So if we apply stress at equilibrium, the system will shift to relieve the stress. So let's say we increase the concentration of reactants on one side. So the system's in equilibrium, but now we suddenly introduce extra reactants on the side. Well, what's the system going to do? Now it's got too much reactant, right? That changes our Q value. Our Q value is now too small because the reactants have grown down here in the denominator. So what's it got to do? The Q wants to grow, so it's got to shift and make more product. Right? What if we reduce the concentration of reactants on the left side? All right. Now this number has gotten smaller, right? So now Q is too big. And if Q is too big, then it's going to break down some products and try to restore the concentration of the missing reactant. So too much A, it's going to try to get rid of A by shifting the reaction toward products. Too little A, it's going to respond by shifting from product back toward reactants to help replace that missing A. So we can predict the response of a system to stresses like adding or removing chemical species, changing temperature, changing volume or pressure, especially with gas, or the dilution of a reaction system. So as we said, here's our example. So if we add H2, right, we increase one of the reactants, it's going to respond by trying to get rid of that extra H2. It will shift toward products, shift to the right. If we remove NH3, right, we're taking away product, the system is going to respond by trying to recreate that missing product, and it will shift toward product to the right. If we decrease volume, Becky, that's going to increase pressure, and so the system is going to shift to the side with fewer moles. We have 4 moles on this side, 2 moles on this side. If we squeeze the pressure down, right, the system's going to respond to that increased pressure by trying to relieve that pressure and repackaging from 4, which takes up more space, to 2, which takes up less space. Conversely, decreasing pressure, right, the system will respond by shifting from the side with fewer moles to the side with more moles to help take up that extra pressure or that extra space. This causes a little bit of grief if we increase temperature. Okay? So notice here, temperature is a product over here. This is an exothermic reaction, so think of temperature as a product. If we increase the temperature, we're increasing product. And so the system is going to respond by shifting to get rid of that extra product, to get rid of that extra heat by shifting toward the endothermic direction. So adding heat, one way to remember is adding heat always benefits the endothermic direction, right? So the reaction in this direction is exothermic. So if we add extra heat, it is going to benefit the endothermic direction, and that heat as a product will be converted back into reactant to reduce, to get rid of that extra heat. If we add a catalyst, it will have no effect because remember, catalyst just speeds up the rate, but the forward and reverse rate are equal, so it will just speed them up equally and will have no net effect. So again, some quick summary of Le Chatelier's principle. We increase any of the substances, it will shift away from the substance. We decrease any of the substances, it will shift toward it. We increase the pressure of a system, it will shift towards fewer moles. We decrease, it will shift towards more moles. If we increase temperature, it will shift away from heat. If we decrease temperature, it will shift towards heat. If we add a catalyst, no shift whatsoever. Remember, the catalyst lowers the activation energy in both the forward and reverse directions, changing the rates equally, so it has no effect on equilibrium. It will help a reaction reach equilibrium quicker, but it won't change the equilibrium or the equilibrium constant. Remember, the only thing that does that is temperature. What if we add an inert gas? Okay, one that doesn't react with any of the components of the reaction. Well, that is going to increase the pressure of everything, but it isn't actually going to change the concentration of reactants or products. So the addition of an inert gas will have no effect on the reaction. Remember, changes in temperature affect the mass action expression, so it changes the K. If we have an exothermic reaction, an increase of temperature makes K smaller. This is maybe counterintuitive until you remember that heat is a product, so it's going to shift back towards reactants and give you less product. K will go down. So increasing temperature in an exothermic makes K go down, whereas increasing temperature in an endothermic reaction, that's the ones that need the extra heat, that's going to make K larger. So again, this is one that often gives people some grief, is how to deal with the heat issue. But just remember, treat heat like any other product. So if we increase the product side, it's going to shift towards reactants. Remember, the only thing that changes K is temperature. We can use Le Chatelier's principle to predict the effect that a stress will have on properties such as pH, or temperature, or even the color of a solution. Let's look at the reaction quotient and Le Chatelier's principle. Let's look at the relationships between Q and K and the direction that the reaction will proceed to reach equilibrium. Okay, remember, when we have a generic reaction, we have a K expression, which is at equilibrium. We have a Q expression, which is exactly the same, but it describes any point in time, including equilibrium. So this can be, all reactant, all product, no reactant, no product, all reactant, or whatever the quotient is at equilibrium. Remember, a disturbance to the system causes Q to change from K, taking the system out of equilibrium. So at equilibrium, right, Q equals K. But if we cause a stress to the system, we're going to change Q, and Q is going to respond by trying to get back to K. So you can also look at that and just say, okay, what's Q have to do to get back to K? Right? If Q is too small, right? If Q, then that would be the case where it doesn't have enough product. Well, then it's going to shift toward product to get back in balance with K. If Q is too large, that means it has way too much product, then it's going to shift to the reactant side to get rid of some of that product until it gets back to K. So just remember, a big K, right, equals lots and lots of products. A little k means fewer products and much more reactants. But this is also true of Q. A big Q has a lot more products. A little q has a lot more reactants. And so it's going to shift to get back to K. Q too small, Q's got to grow. It's got to grow the products. It's going to shift towards products. Q too large, it's got too many products. It's got to get smaller, so it's going to shift towards reactants until it reaches the Q value, the K value. So let's just take a quick example here. Here's our Q expression, right? We're going to leave water out. We've got product over reactants. If we remove this product, right, that decreases Q, right, because now it's product over reactant. This gets really, really small, and so Q is much smaller than K, and so it has to create more product. It's going to shift to the right. Some stresses, such as a change in concentration, cause a change in Q only. But if we change temperature, that and that alone causes a change in the K value. In either case, the concentrations or partial pressures will redistribute to bring Q and K back into equality. All right, the final couple of topics are solubility and common ions. And we can talk about salt dissolving, and that's another reversible process. And that can be influenced by environmental factors such as pH or the presence of other dissolved ions, known as common ions. So let's look at how to calculate the solubility of a salt based on the value of what's known as KSP, the solubility product constant. So the solubility product constant is just like any of the other constants, right? So let's say we start here with a solid, and we see that it can dissolve into these ions. We would write a equilibrium constant, right? We would put products raised to their coefficients over reactants raised to their coefficients, but in this case, this is a solid. So we take it out. So this equilibrium K, we can actually just say, it's really just the product of our products, right? It's just our products multiplied together. So we're going to call this, instead of an equilibrium constant, we're going to call this a solubility product, because we're leaving out our reactants because it's a solid, and we're simply considering our products multiplied together. So in any reaction where we have a solid, our Kc expression reduces to what's known as a Ksp, a solubility product constant. And it tells us the ion concentrations in a saturated solution. So these values are going to tell us exactly how much of those particular ions you can have before they start to go back into solid. If there's more ions than can be dissolved in the solution, then they will precipitate back. And so you can often look at the ion concentration, which we call Q. If the ion concentration at QSP is higher than K, then the ions are going to shift towards the solid form. They're going to precipitate out of the solution and lower the Q until it equals K. So we can calculate the solubility of KSP just the same way we do for KP or KC. And that relationship can also predict the relative solubility of different substances. So we can look, and what we'll see, just like K values, right? Numbers that are very, very big are going to indicate basically complete dissolution. Numbers that are very, very small are going to indicate very, very slight solubility. The smaller the number is, the less concentrated the ions are in a saturated solution. So K values greater than 1 correspond to very soluble, essentially 100% dissolvable salts. K values that are less than 1 indicate only slightly soluble. The common ion effect tells us that the solubility of a salt will decrease if the ion that the salt would dissolve into is already present in solution. So it will go down because there's already ions present, and according to the Chatelier, that is going to make there's already more product there than there otherwise would be, and that's going to shift the solubility towards the reactant side, which is the solid side. So less salt will dissolve if one of its dissolved ions is already present there in the solution. This is known as the common ion effect. We can understand it qualitatively through Le Chatelier's principle, or we can calculate it from the KSP of the dissolution process. All right, finally, we come to pH and solubility and what effects they have on the solubility of salt. The solubility of salt is pH sensitive when one of the ions is a weak acid or a weak base. And again, we can understand these using Le Chatelier's principle. The calcium carbonate is slightly soluble. It breaks down into calcium ion and carbonate. If we add H plus, or the hydronium ion, this is an acid. If we add this hydronium, it will react with the carbonate, and it will basically take it out in this process. It will take it away and turn it into carbon dioxide. So the addition of this acid reduces the CO3, which again, Le Chatelier would say, if you take away this product, the system is going to respond by more calcium carbonate dissolving to help replace that removed carbonate. And that's what happens. So the net effect of adding an acid is we remove more CO3, which causes the equilibrium to shift to the right. And so more of this will dissolve than otherwise would dissolve without the acid. Okay, so quick review of factors that affect solubility. For solids, as temperature increases, solubility goes up. If we add either one of these ions to this solution, then our solubility is going to decrease because Le Chatelier says it will force them back into the solid form. They'll precipitate out because their concentration is too high. Q is too high, it will shift back towards reactants. pH, if they have basic properties, then an increase in acid will absorb, will take away some of those ion products, forcing the reactants to dissolve more to replace them. So if they have basic properties, their solubility will increase as the solution becomes more acidic. Okay, finally we can talk about the free energy of dissolution. When things dissolve, we can see changes in both the enthalpy, that's the energy, and the entropy, that's the disorder that occurs in that process. And we can look at the free energy change, the delta G, for dissolution. And that's going to be the combination of three factors. So we're going to have to break the intermolecular forces that hold the solid together. Then we're going to have to reorganize the solvent. So we're going to have to break apart the solvent to get around the dissolved species of the ionic compound. And then there's going to be the interaction between the solvent and the dissolved ions of that compound. So here's, from an energy point of view, here is what we have to do. So we have to invest some energy. This is an endothermic process. We're going to take the solvent and we're going to separate the solvent. So that means we have to overcome the IMFs in this solvent. Then we have to separate whatever it is we're dissolving, our ionic compound. And that too requires an input of energy. So energy to separate the solvent, energy to separate the compound. Okay. Now, when we let these separated particles come back together, right, that's going to release a certain amount of energy. So this is somewhat similar to our Born-Haber, right? Energy to break, right? But that we get energy freed when we make. And if we get more energy back, then that's an exothermic solution formation. If we don't get the energy back in that third step, then it's an endothermic solution formation. But in either case, the steps are the same, right? We break apart the IMFs of the solvent, we break apart the IMFs of the compound, we let them slam together, and that releases a certain amount of energy. We can estimate the sign and magnitude of the energy changes as well as the entropy changes for each of these factors, right? So as you can see, this is much more organized. This is very, very organized. So when we break those apart, which costs us energy, we are going to get an increase in entropy. So the entropy will increase when we break the solvent apart. The entropy will increase when we expand or break the compound apart. Then when we mix them together, our entropy increases even more. So the entropy is going to generally increase as we dissolve things, whatever else the enthalpy may do. So it usually costs us energy to get to do these steps, but we can pay for it sometimes with an increase in entropy. Remember, entropy means less randomness. So we go from an ordered state to a less ordered state to a far, far less ordered state in solution. So randomness will increase as we go into solution. Just different ways of looking at the, obviously, here's order of our compound, here's the order of our solution or solvent, like water, and then when we hydrate these, we create a much more disordered system. However, making predictions for the total change in free energy can be challenging because there are cancellations among the free energies associated with the three factors, right? Because we can see here, in this step, this is going to cost us energy, but we gain entropy. Cost us energy, but we gain entropy. Okay. Down here, we're going to gain energy, but who knows what's happening here with entropy. So the key concepts for this chapter. Reactions are usually reversible, and reactions that can proceed in both the forward direction and the reverse direction will eventually settle down where the rate in the forward direction equals the rate in the reverse direction, and that's known as equilibrium. At equilibrium, there are no observable changes in concentration or pressure of the reactants or products, and yet it doesn't mean that the reaction has stopped. It means that the forward and reverse rates, which are continuing to happen, are in balance. The cannonballs being fired from both armies are in the same rate, and so there's no net change of cannonballs from one side to the other. The forward reaction, if that's favored, it will produce products. This is often the case when we only have reactants, no products. The forward reaction will be favored and it will produce products. If we only start with products, then the reverse reaction will be favored and it will flow towards reactants. At equilibrium, both rates, both the forward rate and the reverse rate, are equal to each other. We can describe this situation with using an equilibrium constant, which is usually a Kc of molar concentration or Kp of partial pressure. We can also describe these things with what's known as a reaction quotient. And at equilibrium, the K value and the Q value, the equilibrium constant and the equilibrium quotient will be identical. K tells us at a glance whether products or reactants are favored. A K value that's much, much greater than 1, basically 1,000 or more, will produce more products. A K value of less than 1, basically 1,000th or less, will produce more reactants. Something in between that, something between 1,000th and 1,000, we consider that to be around 1, you will have roughly equal numbers of both. If we reverse a reaction, it's the same as inverting our K and our Q values. If we double the reaction, it's the same as squaring our K and Q values. Triple the reaction, we cube our Q and K values. If we add reactions together, it's multiplying the K values of each of the individual reactions. The Chatelier's principle says a system in equilibrium will respond to stress by trying to get back to equilibrium. The only thing that changes K is temperature. That's why we call it the equilibrium constant. If Q is larger than K, that means that we've got more products than the system wants. At equilibrium, then it will shift left towards reactants. If Q is much, much smaller than K, then the reaction will shift to the right. I like to write K before Q because then the arrow points in the direction of the shift. Right? If Q is bigger than K, the reaction is going to shift toward reactants. If K is bigger than Q, the system will shift to the right towards products. A KSP of greater than 1 indicates very soluble salts. KSPs less than 1 indicate only slightly soluble salts. And that solubility is affected by the presence of a common ion. That will reduce solubility. And pH will increase solubility if it takes one of the species out of the products. That's all. Thanks for your time.